Hey there, and welcome. Ever wonder if you could hit undo on a math problem? Well, today we're diving into the secret world of invertible functions to find out. And trust me, this isn't just a puzzle for math class, it's the core idea that keeps our entire digital world safe. I mean, really think about it for a second. Every single day, we're sending super sensitive information online, and we barely even think about it. So, how does all of that data stay private and protected? Well, the secret sauce is something called encryption. Your info, like that credit card number, gets scrambled into a secret code using a really clever mathematical function. Then, the bank on the other end uses a sort of key function to unscramble it. But for this whole thing to work, it has to avoid one major weakness. Just imagine the chaos. What if my credit card number and your credit card number got scrambled and turned into the exact same secret code? The bank would have no clue who actually bought what. The whole system would just break. And this is exactly why we need a very specific, very special kind of function. So to get around this huge problem, we need what are called one-to-one functions. This idea is, quite literally, the foundation of secure communication. Okay, let's break this down. Over on the left, you've got our heroes, the one-to-one or invertible functions. The big idea here is that every single output or y value is paired up with exactly one input or x value. It's a perfect match. But on the right, you see the many-to-one functions. Here, one y value can come from multiple different x values, and that's the kind of confusion we absolutely have to avoid. Okay, that's the theory, but how can you actually spot one of these special functions just by looking at its graph? Turns out there's a super simple visual trick for that. It's called the horizontal line test. And the rule couldn't be simpler. If you can draw a single horizontal line that crosses the graph in more than one place, the function is not invertible. And why does that matter? Because it means that one output value could have come from a few different input values, which creates that messy ambiguity we talked about. You know, the best way to really get this is to just see it in action. So let's play a little game of pass or fail with a couple of functions you've probably seen before. All right, first up to the plate is a classic cubic function. Take a look at that S-curve. What's your gut feeling? Is it going to pass the test? All right, let's put it to the test. Just imagine you have a perfectly straight horizontal line, like a ruler. Now, in your mind, slide that ruler up and down the entire S-shaped curve of this graph. Pay close attention to how many times it crosses. And what do you see? No matter where you put that line, it only ever touches the graph at one single point. It totally passes, with flying colors even. This function is one-to-one, and that means it's invertible. All right, next up, the absolute value function. It's got that classic V shape. So what do you think? Invertible or not? Let's see what happens. If we draw our horizontal line pretty much anywhere above the x-axis, let's say at y equals 2, uh-oh, we hit a snag. The line hits the graph not once, but twice. Once at x equals -2, and again at x equals +2. And this right here is the whole point. If I told you the output from this function was 2, you would have no way of knowing for sure if the original input was -2 or 2. That confusion, that's what makes it impossible to reverse with any certainty. So this function is not invertible. It fails the test. Okay, so the visual test is awesome and super handy, but sometimes you need something a bit more rigorous. For that, we turn to algebra. The logic goes like this. You start by assuming that two different inputs, let's call them A and B, give you the exact same output. If you can use algebra to prove that A and B had to be the same number all along, then you've proven the function is one-to-one. So let's walk through this step by step. For a function like 3x minus 5, we start by setting the outputs equal. 3a minus 5 equals 3b minus 5. Simple enough. Then, we add 5 to both sides, which gets rid of the 5's and leaves us with 3a equals 3b. Finally, divide both sides by 3, and we're left with a equals b. Since the only way the outputs could be the same is if the inputs were the same, boom, we've just proven this function is one-to-one. Now, this horizontal line test is a fantastic tool, but there are a couple of classic mistakes people make, so let's make sure you don't fall into those traps. So let's clear up two really common points of confusion. First off, don't get your line tests mixed up. The vertical line test just asks, hey, is this even a function to begin with? But the horizontal line test asks a much more specific question. Okay, it's a function, but is it an invertible function? And second, be careful with those flat, constant functions. A line like y equals 5 is definitely a function, but it fails the horizontal line test, well, infinitely, so it can never be inverted.
And that, my friends, brings us right back to where we started. See? This isn't just some abstract thing you learn in a textbook. The security of your online purchases, your private messages, pretty much our entire digital lives, all depend on this one simple principle: math that's not ambiguous and can be perfectly reversed.
When you strip everything else away, the whole idea of an invertible function boils down to this one simple, powerful relationship. One unique output for every one unique input. It's this perfect pairing that guarantees any secret code can be unscrambled perfectly with zero confusion. So that leaves us with a really cool question to think about. We know it's crucial for credit cards, but what other parts of our digital world, the things we use every single day, absolutely have to be built on this same foundation of perfect mathematical reversibility? If you start looking for it, you'll realize the answer is pretty much everywhere.